So after a couple of the digital talks, let's now move on to several analog talks, which will be moderated by Priya from Yale.
Hello, everyone. Yes, we are off to the analog session, and we have a great speaker to start off this session, which is Professor Gert from University of California, San Diego, and he'll be talking about his perspective on energy-efficient neuromorphic learning and inference, focusing on how we can actually achieve greener AI on the edge using spiking. Gert, please go ahead.
Thanks, Priya. Okay, so we live in very exciting times, and everything seems to be going very well for machine learning. We get all these tremendous advances in the performance of machine learning systems and AI, but those come at tremendous costs in the amount of computation that's required. Just this order of magnitude of computation increases just for a few percentage points in accuracy. And clearly is not tenable if you look at the amount of energy that this all consumes. So this really calls for different, greener, ecologically more tenable approaches to artificial intelligence and computing. And so for that, we take inspirations from how the brain does it. So to contrast, basically the kind of the achievable limits of efficiency that you get, basically the Landauer limit, which is about kT, which is the Boltzmann constant times temperature for each bit of computation, versus the amount of energy consumed typically by a computation in a typical digital system. Those are about more than 10 orders of magnitude different. So we definitely have lots of room for improvement. And if you compare this against the brain on this log scale of efficiency, clearly the brain is a lot greener and consumes about a femtojoule per synaptic operation, basically neurons spiking about 10 hertz, 10 to 15 synapses, so that's 10 to 16 synaptic operations per second at about 10 watts of metabolic power. So clearly there's a lot improvement that can be made in digital computing, and so far we haven't gotten too far, even with the latest advances in GPUs and FPGAs, which are great for what they do, but in terms of efficiency, they're mostly limited still by mostly serial access to memory. Well, even with high bandwidth memory, still they're quite limited due to the fact they still have to move data back and forth. In contrast, compute in memory approaches can really give much greater efficiencies in the order of about picojoules per Mach. And so remissive neuromorphic approaches, as we'll be talking about, can further improve those efficiencies in the closer to what the human brain is doing. And in fact, some adiabatic energy recovery techniques in charge domain computing can even do better than that, even beat the efficiencies, nominal efficiency of the human brain, and also briefly touch on this today. Of course, we have to be very careful how we assess the amount of computation that is performed and the cost associated with it, because after all, we have to accomplish a certain task. And so it's important to then look at task complexity, right? How hard is a task to be performed versus the machine complexity, right? What is the cost that is paid for doing that computation? And so for many years, Moore's law has really given great advances, right, in machine complexity, in this case, density of compute. And we had mostly linear advances in basically task complexity due to the fact that most of computation was exact. So there was basically parity for computation versus the amount of the state space that can be covered. And deep learning has really bent this trade-off towards more collective analog computation. And neuromorphic engineering now has a means for even, right? So even also getting at greater efficiencies for doing so, where then tentatively we can get at human brain level computation at comparable power budgets. It's important to really then consider all the different factors in this for efficiency. Energy per task decomposes in energy per operation times operations per task. And so neuromorphic engineering can really push the efficiency by doing this compute and memory approaches, bringing the memory much closer to the compute and vice versa. whereas some algorithmic approaches to deep learning and neuromorphic extensions to that can really also then lower the operations per task. And in order to do so, it's very important to consider the massive scale at which computation needs to be performed and how data must be moved around or represented. And so it's important to model both the flexibility of connectivity of say, a neural network versus the expandability in order to implement very large tasks. And those naturally align with, the flexibility aligns with the gray matter, right, of basically the synapses that you have, basically arbitrary connectivity through synaptic connections, whereas the expandability is covered basically by the white matter of the brain, right, so the long-range connectivity. And so hierarchical approaches for this long-range connectivity through hierarchical address event routing really offer both advantages of expandability while still offering this flexible interconnect of the gray matter, right? So this white matter of higher that can also then cover the gray matter with flexibility of synapses. And so at the synaptic fabric, right, you can have this crossbar arrays of synapses, right? So basically very tight coupling between the memories and the compute elements where in basically order one, basically instantaneously, an entire matrix vector multiplication is performed. And in addition to allowing this great density of and high efficiency of synaptic interconnects, this also provides for online learning, right, with synaptic plasticity, both biologically inspired rules such as STP, as we heard about, as well as extensions, which we'll also hear about later. And so, you can have those crossbar arrays of synapses on top, right, in these nanotechnologies, right, on top of CMOS, implementing then the arrays of neural elements as well as, right, this fabric of interconnecting then those neurons on a larger scale through this hierarchical address event routing, where correlates, right, with this neurosynaptic cores, right, are then interfaced with other elements on a grid or in a hierarchy, in a tree for long-range connections. And so here's what we implemented in both CMOS standard silicon technology as well as RRAM, or resistive random access memory, on top of it, where we have this direct coupling between this memory and compute elements, but also have this bidirectional configuration where we can have bidirectional transport or bidirectional configuration of the traffic of neural state variables across this network, right, and allowing to do transposing of the connectivity in the network. This is extremely important for, say, doing backpropagation learning, or also have this different, basically predictive Boltzmann machine or autoencoder structures for efficient generative learning. And so doing that can be done at great efficiencies, down to femtojoules per network operation, owing to this close coupling between memory and compute. And then, so by having 48 of those cores on a single chip, we were able to really get three very important aspects of what it takes to bring edge AI at performance levels that are required. Right? So both high versatility in being able to reconfigure all these different cores and their internal elements for doing not just one but multiple tasks in AI, while having great efficiency in doing so, and also really then still getting efficient accuracies that are comparable to digital implementation in standard GPU or other implementations. And so this can be further pushed towards even greater densities and efficiencies by then combining those crossbar arrays with charge domain computing, and even recovering then the electrostatic energy of driving the lines by coupling this with inductors on the other side for really basically doing adiabatic energy recovery, where then the efficiencies can be even brought further, even beating in principle the efficiency of the brain, lower than a femtojoule per multiple accumulate, which we demonstrated many years ago, or even now gives a factor 10 greater if once you go to more advanced technologies. And so our systems that we develop are also catered to the community. So we all participate in this Telluride Neuromorphic workshop every year, And so we're then casting the advances of large-scale reconfigurable neuromorphic computing to the community. We had a great workshop last year and over the last 2 years, and we'll continue doing that. And so this reconfigurable neuromorphic computing fabric is also available to the community over Neurosciences Gateway, so people can just play with that. And with that, I'll just take the questions.
Thank you so much, Gert, for that wonderful talk. I know it was short, but I think maybe we have time for probably one question, and there are a couple of other questions for you on the chat. Maybe you can answer that on chat directly. But Fabrizio Otati has asked, how does the reliability, circuitry, and hence energy involved with analog computing, especially with memristive arrays, impact the chip efficiency when compared to digital chips like Loihi? And he's particularly referring to device endurance, sneak currents, and so on. So if you can just give an idea on that.
Yes, so absolutely. And so I'll point to this paper, right, where we described how we actually, by through chip-in-the-loop training, adjusting the strength of the synapses, we're able to actually get very close to the efficiency and very close to the efficacy of digital compute. But it was not easy, so we had to really train chip-in-the-loop one layer at a time. And I'll point to that paper for this Nature paper that just was published just recently for more information. I'll be happy to answer more questions online. Thank you.
Thank you so much, Gert. Thank you. Let's move on to the next short talk in this session. And the next short talk is by Alexander TIMOFEEV from Polyn Technology. And this talk is going to be on the role of neuromorphic analog computing in solutions for industry.
Yes, my name is Alexander TIMOFEEV, and I am CEO of Polyn Technology. We are focusing on development of a new neuromorphic hardware. And what is the problem we solved? Look around. In new IoT era, the billions of sensors generate digital data tsunami. And we need solution to move data processing directly to on sensor level, like biosensor, like our brain and eyes do this. This problem is critical for IoT wearables and autonomous devices. And few digital neuromorphic accelerator perfectly work on data centers level, but it's still a problem to support neuromorphic data processing on tinyAI level, especially if you need always on and real-time application support. And analog neuromorphic solution can be work perfectly in that level, but still available practical solution, the ready product today. And we introduce neuromorphic analog signal processor. That is a new platform to make analog neuromorphic in practical reality today in various products. What is the core of our technology? What is the idea? We use fundamental property of deep neural net training. After a few hundreds of thousand cycles of training, the 90% approximately of neural net layers are become frozen. And just the final layer is still updated for classification. And the reduced data vector between fixed and flexible part is called as embeddings. It's 1,000 times less than input vector size. So we use this property to use our own EDA platform, and we do conversion of any trained neural net to our own proprietary format, and then to use analog single neuron for physical design of neural core. So that this is direct generation GDS files from digital neural net to chip layout. And we represent neurons as analog blocks and weights as a resistors array. And that analog structure, analog neuromorphic structure, it's 100 times more energy efficient than the digital core with the same data flow up to microwatt level power consumption in real-time data processing. And that is focused on, again, to sensor level data pre-processing, not for brain functionality for that. And that give us a very high efficiency and this tinyAI application. I just want to explain the one of the application where we can use this NASP core, that is predictive maintenance data pre-processing. For predictive maintenance industry now try to switch for wireless sensor node, but the biggest barrier here is a huge data transfer, because vibration, raw data, vibration sensor generate megabytes per second data. If we use our concept to convert pre-processing core to analog neuromorphic chip, to NASP core, and shift data pre-processing to sensor level, we can dramatically reduce data transfer up to 1,000 times. That's what I mean before on embeddings description. So we can use only embeddings for machine learning cycle. So we keep the same idea of machine learning cycle. We have a cloud-based classification layer in digital environment, but we reduce dramatically data flow. So with pre-processing, it shifts to ultra-low power neuromorphic analog core directly on sensor, and just few kilobytes of data transfer to classification head in small model of neural net based on digital cloud. That opened a lot of opportunities, enabling technology for energy harvesting sensor nodes. We can offer for industry AI sensor node with dramatically lower cost using low power network communication like LoRa or others. So it's an open wide range of new applications, not only high-end application like today in airspace or energy, but also for fleet management, and can generate a new ecosystem of predictive maintenance for industry where don't use before that technology. So that is a summary of benefits of this solution. We can, again, using our ultra-low power analog neuromorphic core, we can support full up to 20 kilohertz bandwidth of input signal, which is today it's not possible for digital system because the data flow is too high. And we can work in approximately below 100 microwatt power consumption, including data transfer. So that is possible for energy harvesting technology and use any IoT wireless communication technology. So that is an example of practical implementation of analog neuromorphic core that is not a lab. So our platform works. We already built first engineering chip, and that product chip, VibroSense, will be available, I hope, in second part in next year. So that is what we're doing.
Thank you so much, Alexander. Thank you so much for your interesting talk and showing us some of the nice works that is happening. So maybe one question that probably Paul Ditterer gave away at the very beginning of your talk was, how many synapses could you implement on this particular chip?
And that chip is approximately, we are not operate synapses, but they consist of approximately 50,000 of physical neurons and few millions parameters. Got it.
Okay, so maybe there aren't any questions, and since we have one question for one, time for one question, maybe I can ask something that I was wondering about is, are you also trying to think of a technology to, because you're talking about this agnostic to wireless communication technology, are you thinking about how you can look into sparsity from these computations in general and try to have sensors, these wireless sensors that can take advantage of it while you are, of course, you are saying it's agnostic, but still, do you think that can be a more whole-ended solution if you look into the sensor and the wireless side of things and look into the sparsity of it?
It's application-specific standard product. So we create the few lines of product which is focused for sensor type. First, it's a piezo sensor for vibration signal. Next product, it's focused for more medical sensor like PPG, and other medical device for wearables. The third line, it's a voice processing. We can take any type of microphone, MEMS, analog, or everything about voice processing. So it's a separate lines of product because your model and neural net for voice processing, for example, it's require different training and different expertise. So we create platform which can convert digital model to analog neuromorphic core. And then we cooperate with different partners who have experience in various neural net. So we have today 3 lines of partners, and we are open, so we can convert any type with no limitation, any type of convolutional, recurrent, any type of neural net.
Got it. Thank you so much. So the next short talk is by Sumeet Kumar from Innatera, and he will be talking about spiking neural networks for sub-milliwatt AI at the sensor edge. Sumeet, please go ahead and share your screen.
So my name is Sumeet. I'm one of the co-founders and CEO of Innatera. Innatera is a Dutch semiconductor company, and we enable ultra-low power intelligence for sensors. We spun out of the Delft University of Technology back in 2018, and we're headquartered here in the Netherlands. We have another center in India, and it's from here that we're actually building what we think is the next generation of tinyML for the sensor edge. Today, if you look at the overall AI value chain, this is roughly the picture that you see. On the left side, you have the sensor, which produces a lot of data. And on the right side, effectively, you have the data center where much of the world's heavy lift machine learning models are currently run. Typically, the design constraints that you see for processors that treat this data, treat the sensor data on its way to the cloud, tend to vary quite a bit. In the data center, especially, the objective tends to be a lot on throughput. But the moment you come closer to the sensor, the kind of application which you run on processors, the kind of application that you try to implement on sensor data becomes more specific. But more critically, the amount of power that's available to do this work becomes more narrow. And absolutely at the sensor edge, the latency of applications is also very critical. This is really the space that Innatera focuses on, that is bringing intelligence to the sensor and the chips in the immediate vicinity of the sensor itself. We do that with the spiking neural processor. This is essentially a brain-inspired processor that enables turnkey intelligence in applications where power is limited. It allows you to analyze sensor data in real time to detect and identify patterns of interest. We typically tend to focus on applications which have an always-on nature that can utilize the event-driven processing capabilities of the spiking neural processor. And such applications also tend to have a very narrow latency envelope, which is generally of the order of a few milliseconds, and also a very narrow power envelope, which is often a milliwatt or less. The way we fit within these very aggressive KPIs is by mimicking how your brain recognizes patterns in sensory data, and that is using something called a spiking neural network. The best way to think of a spiking neural network is that it's a neural network with a notion of time. Inside this neural network, data is represented using very simple voltage spikes, which have a precise timing. That is, it matters when these spikes occur. And the way the neural network works is by manipulating these timing relationships between the different spikes. And by doing that, you can either classify sensor data coming in, you can extract features from that data, or you can even change the characteristics of that data itself. This notion of time is very powerful. It is what allows spiking neural networks to implement the same function for which you often require a deep neural network, which is up to 100 times the size of that SNN, which means that these models can be really small and efficient. What Innatera does is develop accelerators for these spiking neural networks. This is the architectural view of the spiking neural processor. What you note on the left is a set of standard sensor interfaces that allow you to connect sensors in a standard way to the chip. You see a box in green, which allows you to convert standard sensor data into the spike-based representation, which our SNNs can understand. And on the right side, you see the blue box, which essentially has programmable neurons and synapses that allow you to carry out inference of spiking neural networks in a massively parallel fashion within an ultra-low power envelope with ultra-short latency. This processor allows you to process sensor data with up to 500x lower inference energy and up to 100x shorter inference latency compared to conventional neural network approaches running on deep learning accelerators. All of the complexity of our hardware approach is masked by a very powerful software development kit called TILAMO. TILAMO really allows you to develop spiking neural networks directly in PyTorch without any of the complexity or the expertise which you typically would have required in the past for developing spiking neural networks. So if you've developed neural networks, you can use TILAMO and you can readily start developing for our platform as well. Once you've built your model in PyTorch, you can simulate your model using an architectural simulator that serves as a stand-in for our chip. And once you've found a model that you actually want to take to hardware, you can map that onto our chip using our compiler. So this is really a very simple turnkey and standard SDK, and it allows you to very quickly deploy very powerful algorithms to your edge applications. To show you what we're actually capable of doing, what you see here is an implementation of audio classification on our analog chips. We do this with a very tiny spiking neural network model with not more than 100 neurons and a few thousand parameters. The activity of this network itself is extremely sparse, as you see at the bottom left corner of the screen. On the right, what you see is a live demo of this audio classification task running on our chip. We are capturing data from a microphone, pushing that onto the chip, and the chip is essentially running a trained model that is detecting these keywords. And it does so in an extremely competitive fashion. Compared to a tinyML CNN running on an ultra-low power deep learning accelerator, we have a 400x lower energy per inference. We have a 1.4x shorter inference latency, as the approach that we're comparing to is very competitive already on the market. And we still do this with a 4x smaller model, which is extremely tiny. And that's really what makes Neuromorphic the next generation of tinyML for the sensor edge. I hope this presentation gave you a glimpse of why the spiking neural processor is so critical in bringing this unprecedented power and performance of analog mixed signal computing to the edge. And I hope it gets you interested in the TILAMO SDK, which really makes spiking neural network development more simple and more accessible to all. We do have a partner program at Innatera, which does provide early access to our silicon and to our SDK to partners. And this will allow you to experiment and develop ultra-low power AI applications based on spiking neural networks. If this is something that interests you, please do get in touch. Thanks a lot.
Thank you, Sumeet. This was a very nice talk. We do have one question from Venkat Rangan. PyTorch limits the kind of models that can be described as compared to what can be run on a spiking system. What are your thoughts on them?
So I think it's very important that, you know, while we're developing these very efficient AI technologies, we're aligned also with what industry wants to do with them. Mimicking biology, mimicking the brain is not really the objective for all. Our objective really is to take spiking neural networks and apply them to real world problems. And very often these problems require tangible solutions, which are also what you see expressed in standard machine learning frameworks. I'm not saying that the framework has everything that it needs to, but this is where we as a community come in to actually extend those frameworks with what we think it ought to have. And this is what we've done with our extensions as well to PyTorch, to give it new capabilities that allow you to fully leverage the capabilities of analog mixed signal hardware like ours.
Thank you, Sumeet. There's one more question. Does the chip allow for on-chip training? If not, do you think that it is better to rely on a digital on-chip or onboard processor like a RISC core that you have shown? And this question is from Fabrizio Otaki.
That's an excellent idea. So at the moment, a majority of the applications that we do focus on really target inference at the sensor edge, but there is a growing number of applications which do require on-device learning, and this can also be supported on our chip. Exactly how you implement them, exactly what kind of learning rules you use, I think there's a lot of diversity and options there, and of course, we'd be happy to discuss this together with you.
Thanks, Sumeet. We will move on to our next talk. And again, this is a short talk. This is going to be by Gordon Wilson from Brain Neuromorphics. And Gordon is going to be talking about what comes after digital, the path forward for brain-like AI.
Great. Thank you all so much. It's good to be here. Hello from San Francisco. I'll try to get through my slides pretty quickly so we can get the whole story. But we are RAIN. We are the Artificial Brain Company, and it's great to be here. We're a story of outsiders. So we started in the swamps of Florida, specifically the swamp, the University of Florida. Started this company with my CTO when I was 25 years old. We're fairly unique within the world of AI chips and neuromorphics in the sense that we don't have PhDs in our field. We are truly outsiders. I think we can bring a fresh perspective. And over the last 5.5 years, we've become backed by world leaders in artificial intelligence. Most importantly, Sam Altman led our seed round. We've partnered a lot with OpenAI, who's our neighbor here in the Mission in SF. And they've been a fantastic research partner and development partner for us over the last several years. Now, let's talk about brains. Brains learn efficiently. Brains learn. Brains can adapt from new information. They can continuously take in new experiences. And this is really what makes brains particularly special. But not only can they learn, but they learn efficiently. They do so with very few examples. They do so with very little power. They do so in an extremely small footprint. Brains are extraordinary learning machines, but they're also extraordinarily efficient in how they perform that. Our mission at RAIN is to build a brain. And we share that mission with the forefathers of our field. Whether it was Turing or von Neumann, the brain has been guiding this entire field of computing and artificial intelligence for a very, very, very long time. Now, we are in a golden age of artificial intelligence today, and this has not been driven by neuromorphics. But we have some incredible examples that have shown us what's possible in artificial intelligence through deep learning. AlphaFold has predicted human proteins from simply amino acid sequences. DALL-E 2 generative models can now create images that are realistic from simple text descriptions. And of course, ads now drive revenue at Facebook and Google, and the bulk of these ads are driven by recommendation models, also neural networks. The problem here is that all these three incredibly powerful types of neural networks, each of these are backed by companies worth hundreds of billions of dollars. And to train these models and deploy these models costs tens of millions of dollars. So we need a dramatically cheaper and more efficient way to implement this. Today's AI platforms are not brain-like. You really have two options of AI platforms that are commercially available today. You have massive data centers that run GPUs or other types of digital hardware, or you have more efficient types of implementations that may implement mixed signal processing or operate with as a digital ASIC. So you either have the ability to do training with backpropagation and data centers in very expensive models, or you have the opportunity to deploy that with efficiency. But we really don't have a platform that gives us both. Today's AI platforms are not brain-like because they can't learn efficiently. Now, of course, there are many people here talking about learning and talking about things like STDP and other types of learning rules. But the truth is that neuromorphic training, i.e. training with STDP, has never matched backpropagation-based training in terms of performance. We've seen incredible demonstrations of low power, but there's a reason why AlphaFold, AlphaGo, GPT-3, all of these massive models that have shown what's possible in terms of new types of features of intelligence have been developed on backpropagation platforms. This is the problem we're focused on solving. How can we train neural networks in a way that is as robust and as capable as backpropagation, but in a way that's as efficient as these low-power platforms and ideally as efficient as the brain? And we're solving the problem of efficient learning with the luminaries of our field. So two papers I'm going to highlight, one from 2020 and then one that is actually about to be released, kind of highlight our progress in this domain. So in 2020, we collaborated with Yoshua Bengio, one of the godfathers of deep learning, and one of his students had originated an algorithm called equilibrium propagation. And equilibrium propagation was very exciting because it was backpropagation equivalent, but it was biologically plausible. And we worked with Bengio to show that this was implementable in an analog circuit format. This was in the summer of 2020. And this has not yet been fully released, but we have just worked and collaborated with the creator of the first memristers, Dr. Stanley Williams, to now implement this analog learning algorithm on memristers, with memristers for the first time ever. So in both cases, these two papers point to our progress on developing a far more efficient way to learn, but a way that is gradient-based and that is as powerful as backpropagation. Equilibrium propagation is equivalent to backprop, but it trains with a local learning rule. Now, backpropagation has this global learning rule, which means for every synapse to update, you need to take into account the state of the entire network. And as other people have mentioned earlier today, this is a critical reason why this is not biologically plausible. But it also makes it extremely expensive because it means for every weight update of every synapse, you need to differentiate across the entire system. Equilibrium propagation can do the same type of math, the same gradient-based learning, but with a local learning rule. Now, we'll talk a little bit about applications. Artificial brains will power the most important AI applications of the future. Personal AI needs artificial brains. Anything that's going to adapt to our changing behavior, that is going to be using sensitive private data, we will want something that can learn on the fly independently next to us. Remote AI needs artificial brains. If we're going to continue exploring the edges of the universe, we'll need a dramatically more efficient learning because we can't communicate with data centers back on Earth. And of course, safety critical AI needs artificial brains. Now, we've had numerous leaders in autonomous vehicles invest in us because they have emphasized that it is impossible to get to level 5 autonomy in autonomous vehicles unless we have a dramatically more efficient platform for training. Now, we're also partnering with Argonne National Lab to bring brain-like AI to their particle accelerator. We're very excited about this partnership, and it's indicative, I believe, of the demand for this type of intelligence, one that has very robust local learning, but is also extremely low power. So we'll be attaching our chips to X-rays to help perform local learning and dramatically reduce the amount of data that they have to take in and speed up the process of discovery. Now, our roadmap for artificial brains will deliver this efficient learning at any scale. So we have not just been focused on this problem of how do you train efficiently, but we have also been working on developing a more scalable format for this type of analog learning. Now, initial generations will implement resistive RAM crossbars, as people have discussed, but we are then scaling up in 3 dimensions and exploiting a very brain-like architecture that is somewhat similar to a vertical bit-line structure, but really uses sparsity and small world sparsity, scale-free sparsity, brain-like sparsity to connect more neurons and more synapses into single dies than ever before. So this is the other half of our technological portfolio, how you scale in terms of how, as well as how you learn. So ultimately, with a low power footprint, we believe we can concatenate these chips together, exploit things like 3D chiplet integration, put them together like Legos, and truly build artificial brains. Now, quick ending with a metaphor. Today, the best artificial intelligence, it's stuck in the cloud. At RAIN, we're bringing it down to Earth so it can be an animating force for intelligence all around us. Thank you. All right.
Thank you so much, Gordon. That was very wonderful. That was a good end. So we do have one question for you, which you can probably answer from Fabrizio Ottati. He asked that, do you think that for non-human applications, for example, protein structure prediction or accurate recognition for critical applications, does it make sense to follow a non-human approach with universal function approximators like it is being done now, despite their environmental impact? Or do you think that it is possible to build very smart artificial human brains based on SNNs that can efficiently substitute them?
So it's important to reiterate, we are not building a spike-based technology. We are using equilibrium propagation, which is gradient-based learning, but is energy-based. So it's very, very efficient, can be implemented in analog, but isn't using spikes. So really, to your answer, I think the reason why we exist as a company is so we can have both. So we can have something that's as robust as backpropagation, that can train as well as these models have done so far for things like protein structure prediction, but can do so with a dramatically lower power footprint and much less consequences on the environment. I think right now, I mean, there are applications like for medicine that are worth the investment, but we cannot continue down the track of having all of our models built with, that consume, at least the most powerful models, consuming megawatts of power. We need something better.
Got it. Thank you. Thank you, everyone.
So I want to thank all of the speakers for providing such a clear and interactive overview of the field, the Technical Program Committee for putting this program together, and of course you for attending this event. So if you'd like to go beyond today's talks, you will find in the download section of this event's website a PDF file that contains one-page summaries of all the talks that you have seen today. And these also contain some useful references to go further.
This is the list of our strategic partners, starting with the executive ones: ARM, Edge Impulse, Qualcomm, Sentient, and we have DeepLight as a platinum sponsor, Clickertech, Platinum, Reality AI, Renaissance, Sony. Gold sponsors are Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, SenseML, ST Microelectronics, Synaptics, Synsense, we presented today, and we have several strategic silver strategic partners here. And just at the end, if you can go to tinyML.org website, and you're going to see a lot of events happening in this fall and in the next 6 months. Again, thank you again, and we'll stay in touch.